we've got an hour to kind of cover this material. So there's quite a few things to talk about. I know that there's a lot of what might seem like random information with this section. So we're kind of coming from a section that was a little bit more like everything kind of came together with acids and bases to something that seems a little bit more abstract and definitely takes a lot of practice or exposure to feel comfortable with the type of problems. So the first thing we need to get into is just understanding, right now we're dealing with coordination complexes, right? We're dealing with really Lewis acids and bases, and you guys know those definitions of what a Lewis acid and base is from this last exam that you kind of did, right? You studied for that. I don't think it was asked in your exam, but you have that knowledge down. So a Lewis acid being some species that will accept an electron pair, and a Lewis base being a species that will donate its electron pair. So we're kind of looking at these complexes and how they come together, right? Now, make sure you understand that this is different than an ionic bond. Oftentimes we'll see like these positive cations, and we think we can only tack on so many things that will just cover its charge. But that's not really what's happening, only to a certain degree when we see that. And I know you guys are familiar with what I just said, but I just wanted to make that clear. So these are coordination complexes, something that's a little bit different. So there is a complex number, a coordination complex number, and what that number is it tells you just how many things can bond to the center species, right? And each species gets a different number. And these numbers can range anywhere from 2 to 6 or whatever might be given to you. There are a couple that you need to have memorized, right? So make sure you have those memorized. You'll see, I just wrote the ones kind of up on the top of this board, and I apologize for like the wispy stuff on the board just won't erase. I don't know what it's from. So hopefully you can see that from the back. But those coordination numbers to know are chromium 3, cobalt 3, and that coordination number is 6. The fact that he told you to know that is a gimme that I'm sure he'll be dealing with that exact species. Also, platinum 3 is 4, right? So a little bit different. Make sure you have those memorized. What we need to get into is being able to recognize coordination complexes, being able to write their formula or name them, okay? And there's a couple steps that are important when we talk about naming. The first step, anytime we're given a coordination complex, I have written up here, the first thing we need to do is discover what the cation is and understand that we list the cation before the anion, right? And then we got to go on to like, okay, so I know what my cation is, what are the ligands, right? So who can tell me what a ligand is? Just to kind of get some of this, this vocabulary out front for everyone, a ligand. You should be pretty familiar with that. Who could tell me pretty loud so the video can hear as well? Right here in the front.
Something associated with the metal ion.
Right. Something that is bound to a metal ion, right? So over here I have a couple examples, and these are actually some complexes that I'd like to name together, and have you guys name them, actually try on your own for just a minute, and then we'll go over them. But that's what a ligand is, okay? Something that's bound to my metal ion here. So the first step is, what is my cation? And I got to list that before my anion. So what that means is when I look at something like this coordination complex, I see kind of this messy thing. This is one big messy looking molecule that's a little bit intimidating at first, but I need to just break it down systematically and understand, okay, my cation here is going to be my chromium. Okay, so my chromium is my cation, and I know that I list my cation first, right? So I kind of have a part of my name, my cations part, and then I have my anions part. And I immediately notice, like, what's my anion in this case for this whole complex is going to be my chloride, right? So I know immediately chloride goes here. Right, so chloride. And I was looking for my cation, and I know it, it's chromium. I'm going to write chromium. Okay? So once I get chromium, now the rest of it is another systematic approach. You look at step 2, says on the cation side, I need to list the ligands in order of their, like alphabetized, right? Alphabetical order is what I'm trying to say. So basically what that means is I just look at what's there, whatever the letter starts with that name, I list it first. Now, a common mistake is thinking that your prefix is how you list them A to Z. And that's not true. We don't care about the prefix. We don't care about alphabetizing the prefixes, but just the name of the ligand. Okay? So when we look at this, I have a couple ligands here. I have this group and this group that are bound inside the coordination sphere. So anything that is bound inside my coordination sphere is inside of these brackets here, right? So these two species are bound inside. I have this one and this one. Now, what's another important thing to remember about naming? These aren't just your regular names. So you look at it and go, it's ammonia. So I have, what, 3 ammonias. So triammonia, right? That is technically wrong for how we're naming these. You have to know the special names that are given to each one. So we could take a minute and write them all out, but I think your time will be better spent doing that actually on your own, right? So we know that ammonia in this case is amine. And what would water be? Who knows it off the top of their head? Aqua. That one's a little bit more, you guys know that one pretty well. Go ahead, questions?
Is there a source we can find all of those special names at?
Yep, so in the book, they have a list of all the special names, and they also have one, and I think I wrote, like, be familiar with 16.5. I believe that might actually be, like, the part that Corbin's going to go over. But in the book, you'll have a list of all of the names, right? And it's in the slides. That would be my primary place to go. In the slides, you'll see the list of everything you need to know, okay? And kind of have those nailed down. So what would a chlorine atom, what would we name that if it was inside the coordination sphere? Chloro. Okay, yeah, you guys got it pretty well. So over here, I see that I have 3 amines. Now, immediately I know, okay, this is aqua, this is amine. Which one's going to come first? Amine, right? Kind of a close race there, but amine. So here we go. We have how many amines? 3. Tri, right? We want so 3, so tri. I got to be used to also those prefixes as well. So triamine. And then I list how much water. How much water do I have? 3 water, so triaqua as well. It's kind of getting squished here, so hopefully you can see that. Triamine, triaqua, chromium. The last thing I got to do is determine my charge. So what was the charge of my cation? Well, how I do this is I take it systematically. Look at your ligands that are inside the coordination sphere, and you got to check, do those alone bring a charge to the table? Sometimes this requires a little bit of like looking back to your previous knowledge and understanding when I see NH3 alone, do I put a minus or a plus with it? No, it's neutral. So the nitrogens here, or these amine groups bound to my center atom, they're not affecting its charge of how positive that might be. So I got to think, what would? Well, this isn't going to affect my charge at all. With water, I also write that neutral, so that one won't as well. I only am dealing with anything that's on the outside. My anions here are the only thing that will affect the overall charge of this whole complex. I have 3 chlorines here. What's the charge of chlorine usually? A 1 minus. I have 3 of them, so we're 3 minus, right? Overall negative right here. And as a species, the coordination complex is neutral, so what's the charge of the cation? A 3 positive to cancel out my 3 negative here. And we just do that with Roman numerals. Okay? So that would be the name of the first one. So go ahead.
Why do we use try twice and then other times like that?
Okay, we're going to get to that. Actually, I don't have a good example of that on the board. I'll explain it right now then. So there are times, and this is very important, so hopefully you guys really internalize this next principle. There are times in which we use the prefixes that we're all familiar with. Bi, tri, tetra, penta, hexa, those ones that we're familiar with. And then there are times when we use like bis, tetra kis, penta kis, right? Now, the only time you're going to use the separate subset of prefixes is if any one of our ligands, the name of the ligand itself contains one of the normal prefixes. So ethylene diamine, the EN that we normally see, if I was to switch this to EN, right? First of all, that would make the name of this really big, right? But that would change the fact that I use tri over here because my ligand is ethylene diamine. And ethylene diamine looks like this, right? There's this ethyl group and these 2 nitrogens coming off. So there are 2 nitrogens in the molecule, something called di. That's where that diamine comes from. So I can't use diethyl diamine because what that would look like is 2 ethyl groups and then 2 nitrogen groups, right? None of them really bound together. You get confused. Wait, what's together, what's not? That's why I use bis or what is it exactly to make sure? Is it tris? It's not. Yeah, it's tris. And then tetrakis. You guys need to make sure you have those memorized better than I do, obviously. But mostly you use just tris and bis and tetrakis, right? Go ahead, Jin.
Now, we decided this was chromium 3, but isn't that one of our need to knows? Chromium 3 equals 6? How does that-
Yeah, a coordination number, right?
Yeah.
So what's the coordination number of this bad boy?
6.
6. There are 6 things bound to it. Yeah, so this is one that you need to have memorized, and this kind of fits our criteria of what we need to have memorized. So, yeah, so the coordination number is different than the charge. Bring up a valid point just to make sure that's very clear as well. Go ahead.
Can you give us another example of a molecule, like ethylene diamine, that would require us to use bis or tris?
So off the top of my head, it would take me a minute to think of one, just like a random ligand. But just know that the molecule will be given to you. That's one thing. You'll be given what the ligand is and the name of the ligand. If it's something besides ethylene diamine that you're not sure of. And if you're given that name, and you notice in the name it's like triamine, blah, 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 then you know that if I have several of those bound to the center, I need to use my subset of prefixes because the name of my molecule already has one, right? And then if the name of my molecule, my ligand, doesn't have one, like chloro, I don't need to worry about the subset, just use the normal, like trichloro, tetrachloro, that type of thing, okay? So that molecule will be given to that ligand. Go
I
ahead.
think the only two on the table is the ethylene diamine and biopyridine.
Bipyridine. So he says bipyridine. So bi there, we can't. You have to use our subset. So. Okay. So let's move on a little bit. Actually, what you guys should do is take just 2 minutes and bust these out really quickly. Okay. Get the names of those.
This question is something on chloride there, and like the only time you use the ATE is if you're talking about the transition from an anion. Like,
Yeah, try this one.
that's where you use an ATE.
This would be an AT in terms of like what we're writing for this.
Yes.
And then also for polyatomics, sulfate, nitrate, right? So these polyatomic anions that you're used to seeing, like a nitrate or a sulfate or a carbonate, those are used. Yep, but chloride here is what we want to use. Bromide, that type of thing. So yeah, work on these two really quick, you guys, and then I'll plug up the answers in just a second.
Good question. For like the written exam, will we have to like be able to spell these things? Like,
Yeah. Unfortunately, like I would say, yeah, know the spelling for the written exam. Hopefully, what I would imagine, Dr. Macedoni is a really nice guy. I would imagine that he would probably give you the name and ask you to write the formula for something that had ethylene diamine in it. Just had to abbreviate it as EN, right? Probably on that side of it versus doing what we're doing right here. Oh, sorry, I'm just standing there. Actually, maybe if we go right here. Sometimes this makes me have to act like standing for a second. Okay, let's write up the answers to these names, okay? So, we're going to go over these pretty quickly because we have to get to some really important stuff that I think is a little bit more pressing for you guys to understand and know. This is a lot of redundant practice you can do to really nail this down. Now, and another thing, you guys, my opinion on these problems is you should never miss one. You should never miss a problem like this because it's basically a type of reading. It's just like reading a language you're just starting to learn. As long as you learn the certain rules, you can do it. Okay? So please practice enough that you don't miss these problems. Okay? So here we go. This one, I got to figure out what my cation is. It's platinum. Make sure I spell that right. Platinum. Okay, here we go. Platinum. Okay, I have amine here, chloral. So we're going to do pentamine. Chloro. Okay, this is going to be 3. So this is going to be a charge of 4, right? Bromine. So hopefully that's what you got. Double check that's right. Yes. So someone walk me through really quick this one, briefly.
Sodium is a cation.
Sodium is the cation. So our coordination sphere is the anion. So that'll change a little bit of how I name this, right? I'm no longer naming a cation in my coordination sphere. I'm naming an anion, right? But I still do the steps. My cation comes first, which is sodium. So I get sodium. sodium. Okay, now what's my anion here? Well, I have nickel. I have 4 chlorines here. So a tetrachloral in there. And then how would I name the nickel here, you guys? Nickelate, exactly. So it would be tetrachloral nickelate. And then what would be the charge on the nickelate? On the nickel? 2. Good. Okay. So keep the chatter down just a little bit so we can kind of like just keep it a little bit crisper here. Okay, your questions.
So do we have to, like, when we're actually, we're given a name, do we have to write like the nickel chloride 4 in parentheses, like the chloride?
You're given a name.
So like the
You
nickel
wanna-
chloride, like does that need to have parentheses or anything?
This part of it, the tetrachloral nickelate 2, which part?
In the brackets?
In the brackets.
Because like, I just want to know, like, because I know this can get kind of meticulous. And
Yes, the whole coordination sphere is in a bracket, and this is in a parenthesis here. Different, yeah. Is this what, I don't know what your question is.
could you just leave off the parentheses?
On this?
Yeah.
Oh, no, show that.
So
Show that, yeah.
Even though it's.
Okay, that was your question. Yeah, show that. Show that. Okay, so the next part of this, you guys, so we're gonna move past naming. I think you guys can do enough practice with the naming to get that down, but I want to spend the next 10 minutes before we pass over to Corbin talking about isomers. This is kind of like the bread and butter section for understanding and really getting a grip on this test material. Because I feel like isomers is the most difficult thing to understand at first and to visualize them. And so I imagine that isomer problems will be what will separate you from a B and an A, right, on this exam. It'll be probably the problem that will take just a little bit of focus to be able to rotate the molecule and really understand what the pieces are, okay? So let's jump to that. Will you put this one up a little more? Yeah. Keep going. Yeah, I'll tell you what. Keep going. Okay, types of isomers. Okay, there are several types. Okay, the first type of isomer we need to talk about is a structural isomer. So what a structural isomer is something that has the same chemical formula, but the way that it is bonded is different. So the way in which what all the pieces are laid together are different. And a simple example of this, using kind of like a coordination complex looking thing, would be these examples I drew up here. Over here we have the cobalt bonded directly to the nitrogen, right? And then over here, it's bonded a little bit different, right? So this is a type of structural isomer or a linkage isomer, to get a little bit more specific, right? So a structural isomer can show itself in many forms. It doesn't have to be a coordination complex type like this. But it's anything with the same formula, but it's bound a little bit different, right? This one being a specific, a linkage isomer. We're linking in our ligand here to a different piece of what my ligand is, okay? So these are a little bit more simple and easier to understand. The next piece of this, after structural, right, we just have different bonds, so keep that down, is a coordination sphere isomerism. So that's a little bit different than this. Over here, we're just changing what we're bound to, what is our ligand. In a coordination sphere isomerism, what we're doing is we're kind of switching what would be in the coordination sphere when we did those problems up there, what would be in the brackets and what would be outside of the brackets, right? So Dr. Macedoni has a couple pretty good problems on his slides. So I have abbreviated a little bit here to keep it as simple as we can. So these lines you see are just bonds to whatever our ligand is, okay? And I'm specifically switching just a couple of them. So you'll see, so you can kind of plug this information into what you want. But what's important here to realize is this first one, I bound, my iron here is bound to the same ligand all over, right? And I have these bromines swimming around, like in a free solution, okay? They're what would be like on the outside of our coordination sphere for our formula up there. The second one is an isomer of the first because now we've switched. One of the ligands that was bonded, now the bromine is directly bonded and only 2 of them are left swimming around. And over here is just one more. I bound 2 now, and I have 1 of them swimming around. So you have to look at what is directly bound to my center atom and what is like swimming around freely. Okay? So what is inside the coordination sphere when I look at my formula, and what is outside? Okay, so that changes. You guys will notice sometimes when I get these formulas, I will show like a chlorine will be inside, and then sometimes it's outside, right? And if I have everything the same, like all the same makeup, but I'm switching what's inside and outside, then this would be an example of a coordination sphere isomer. Okay, so this one is also a little bit more straightforward and easy to grasp. The next one, let's see, I think, where are the enantiomers? Does this go up, or?
It's on the first one.
Does this go up? You put this up?
Yeah. I think you did it on the first one.
I did. Oh, that's good. So over here, now the next type of isomer, this is the difficult one. This is a stereo isomer. Who remembers learning in Chem 105 about stereo centers? It was so grueling, right? There are a couple rules about stereo centers. Who could maybe spit one out really quickly? A rule about stereo centers. Has everything to do with this? At least 4 what though? They have to be different things, right? So there's any 4 things bound to a carbon. All 4 of them have to be something different, right? That gives me a stereo center, right? And in turn gives me something like a chiral center. And we can get stereoisomers from that. So what a stereoisomer is specifically is the same formula again, right? That's an isomer. The same bonds, actually. It's all the same bonds, but a different arrangement of those bonds. So maybe they're just arranged a little differently, whether or not they're coming out of the page or into the board or down or up, right? All the bonds are the same, but they're just arranged differently. And that's the hard thing to visualize. The easy ones to visualize with stereoisomers are these cis and trans molecules, right? This is a stereoisomer. I do have the same formula. I'm making the exact same amount of bonds to the same things, but in this case, I just switched my double bond here from a trans or an opposite position to a cis, where they're both pointing to the same side. That is an example of a stereoisomer, and that's a little bit easier to see, right? Stereoisomer, you can call it like a category, and inside, under stereoisomer is a bunch of subcategories of types of this, right? So this would be like a geometric type. A cis and trans, like a geometric, it's the same everything except one is just geometrically different than the other, right? So if I wrote this on paper, like the formula, you wouldn't be able to tell unless I told you that one was cis and one was trans. That's kind of the gist of that, right? Enantiomers, now that is another subclass of a stereoisomer. That is the most difficult one to understand. And we need to spend the next 5 minutes going over enantiomers specifically and chirality, okay? So enantiomers, what an enantiomer is, it's a molecule, okay? It has a stereo center in it, and what it is it's a molecule whose mirror image of that is the same bonds, the same everything, except I cannot seem to put those two together. I can't superimpose them. And the best example, the class example is your hands. If I take my right hand and I look at exactly how my right hand is with my thumb and my 4 fingers, my palm facing down. I take my left hand, which is a mirror image of my right hand, with my palm facing down as well. I can't seem to get them to overlap where everything matches. My thumbs are on the opposite sides. So the mirror image is the same, this is correct, right? But I can't overlap them perfectly, which makes this one the enantiomer of this. So an important thing to understand is an enantiomer is not a single molecule. An enantiomer is the mirror image of another one. So in order to classify as an enantiomer, there's got to be a mirror image of you somewhere, and you can't superimpose with that. This is where I've seen a lot of people get confused in the tutorial lab, is the difference between enantiomers and saying is something chiral. Is this molecule chiral, right? So kind of jumping into chirality, and we're going to mix all this together at the end, so hopefully this remains really clear, okay? Determining whether or not something is chiral is not a matter of looking at 2 things together, right? It's not a matter of comparison. It's a matter of looking at a single molecule, right? A single molecule can be chiral or not, and that chiral molecule can have a mirror image that is its enantiomer, right? So you don't have to compare 2 things to figure out if it's chiral. What is something that's chiral? Tell me, what does it mean if I say this molecule is chiral? What does that mean?
There's 4 different attached branches that all look different, and you can't flip them and turn them so they look the same. They have to be structurally different. Right?
Okay, so that would probably make it like some sort of stereo center. But what specifically makes it chiral? Because that will make something chiral. But what is it? What is the defining moment in oh, this is chiral right here?
If you cut it exactly in half and you try and put them both on top of each other, they will not be the same.
Yes, What is the defining moment of what makes a chiral? You guys are like on the verge. This is really important. That is true. So everything you guys are saying is 100% true. Just need one more person to spit it out, right here.
If it doesn't have a plane of symmetry, is that what you're asking?
Almost. I will say it. I will say it. You guys are so close. And like your answers are all right. By no means is this wrong. But what is the defining moment of something is chiral is whether or not it will bend plane polarized light. That is when something is chiral or not. Which is something that is on the slides and we need to talk about, and we need to make sure you understand that. And then we can talk about whether or not, why all the things you guys said affects chirality and determines if something will do that or be chiral or not, right? So what happens here, let's take your question really quick.
Yeah, if you could just repeat that defining moment that you just said.
Yeah, so the defining moment for chirality is whether or not a single molecule will bend plane polarized light. So what that means, if I take a light bulb, okay, and this light bulb emits light. Every photon that's emitted from this light will be in some shape or form like scattered, meaning you guys have seen photons drawn like this, right? Kind of like these amplitude, these waves going on with a wavelength and a frequency, these waves. So some of them will travel like this, but some of them will travel sideways like this, right? Not all of them are up and down like this. Some are like this, some are diagonal a little bit. But when I polarize light, I send light through some sort of film that will only allow the ones that travel in a certain direction to pass through. So everything past that film is traveling all up and down, no side to side or no angle. What happens is I send that light through a molecule. When that light gets to the front of the molecule, you guys have been learning about light being absorbed and maybe shooting photons out like Corbin is going to go over. What happens is maybe that light is altered just a little, right? Maybe it's no longer up and down, just tilted a little. But what happens if it gets to the other side of the molecule? By the time it leaves, it's just back up and down again. When it went all the way through the molecule, it didn't change. It didn't rotate any light. All the light is still moving in the same direction. But if I send light through the molecule and it does change, and by the time it gets to the end, it is still changed, then that means that it is a chiral compound. So how I know if something is chiral is if it does not have a plane of symmetry. If I take a single molecule and I look at it and there's no way I can draw a line and split two halves equal, it will bend light. Because the reason why it won't bend light if they are equal on both sides is when light comes through, maybe it gets tilted one way, but its opposite side is on the other part of the molecule. It will bend it right back to what it did, right? They'll cancel each other out for how they bend light. That molecule will, because it's equal on both sides. So you will not rotate light, right? That's what a chiral compound is, okay? So we got to look at a little bit understanding chiral compounds and enantiomers, right? Any sort of chiral compound can have an enantiomer, right? But not every chiral compound, when you're comparing two of them, you say, oh, this compound is chiral, this one is too. These two don't have to be enantiomers. They can be different from one another. But every chiral compound can have an enantiomer, or a mirror image of one another, right? So we're going to take it really slow with this. We're going to do one practice problem and turn it over to Corbin. So to take it easy real quick, we have this, right? And what I did is instead of drawing different species, I just drew shapes. We're going to keep it really simple at first. And we're going to look at, okay, does this molecule have a plane of symmetry? When I just look at this one alone to determine if it's chiral. And when I look at it long enough, I'll understand it doesn't. There's no way I could draw a line here and split the two halves into even pieces and say, yeah, that won't bend any light. This will bend light because there are no even pieces. So over here, I got to compare these two. This one I drew as the mirror image of this. If I put a mirror right here, I would see that this is an exact mirror copy of that. But then I got to decide if they're enantiomers of one another. Because sometimes the mirror image is just the identical molecule. And how I know if they're enantiomers is if they will superimpose one another, right? If they will superimpose one another, they are not enantiomers. If they will not superimpose one another, they are enantiomers. So this is when the spatial recognition and being able to understand this gets difficult. I have to try to rotate this in my mind to try to get them to be superimposable. And when I do it enough, I'll realize that they are not. Okay, these are not superimposable. So therefore, these two are enantiomers of one another. Okay? So, and I move on to this. Let's look at this one. Again, can I cut a plane of symmetry in this molecule? There's no way I can slice it where the sides equal one another. I look at the two compared to one another now, right? I see this is the mirror image of this. Okay, that makes sense. We're still in this. Now, can I superimpose this one with this one? Now, you still cannot. Now, I'm not expecting you to be able to look at it and go, yes, immediately, or no. It's so hard. It's not easy, so it will take time. Sometimes we use these little models because the models help a ton. Just build one, build the other, and see if you can stack them on one another. If you can't, well, it's an enantiomer. So this is basically the same molecule. I just changed the shapes for actual species here. These are enantiomers of one another. The reason I'm rushing through this, if you feel like we're rushing, is just because we got to get through all the material. Watch this again. Pause the video. Really look this through. I promise you, these do not superimpose. Okay? Quick questions.
Are you sure the first one is not superimposable?
Yes, I'm positive. So, what you can do is pause it and move on. Like when you get home tonight, really look at it and see if you can superimpose them, and you won't be able to. What's hard is the way that I draw these, I'm not a perfect artist, so sometimes if the look shifted a little bit, I'm sorry that you might think, oh, that's definitely going to superimpose, but they will not. Okay? So will you put the board up and we'll do the next problem?
These models you can get in the bookstore.
Yeah,
and
these are
they're cheap, so like does he allow models on the test?
Yeah, I think he said, yeah, he didn't say any or he didn't say otherwise.
You want it down there?
Yeah, so bring the top one down. Yeah, Jim.
Those are stereoisomers as well.
Yep.
Enantiomers, right?
Yep. Enantiomer is a subclass of stereoisomers, so they're stereoisomers, enantiomers more specifically, and each one of those molecules is chiral.
So
Okay?
if it's an enantiomer, it's definitely a stereoisomer.
Definitely a stereoisomer, yes. Okay, let's move on to these problems really quickly, and then we'll get to one last thing, and then I gotta turn the time over to Corbin. I know this is the hardest thing. This is gonna take your own practice a little bit, okay? So, let's work on these two. You guys take a second, and I want you to first compare these two, and then take a second and compare these two, and try to figure out how these work. Whether or not, first of all, is this molecule chiral? I'll skip ahead and say yes. There is no plane of symmetry to draw any of these. Now, when I compare these two, are they enantiomers, or is one the mirror image of the other? Or even if it is the mirror image, right, but maybe I've rotated a little bit to be the mirror image, well, can I still superimpose it, right? Is it superimposable? Then it's not the enantiomer. So take 2 seconds and look at that, and we'll talk about it briefly. Does anybody know? If you start already, this is super fast. I don't expect you to have that down already. Are they enantiomers? No. Raise your hand if you think they are identical. Raise your hand if you think they are enantiomers. Okay. They are identical. So that was good. They are identical. I just changed it a little bit so it's hard to see. But if you build a model, you will see. If you build the one, it's exactly a copy of the other. I superimpose it completely. Now, compare these two. This is a little bit harder. Are these two superimposable? When you go back through this video, you will see that they also are not superimposable, right? Like the problems we just did. So that means they are enantiomers of one another, okay? So the last tidbit is just the fact that if I have enantiomers and I have an equal amount of both, what type of mixture is that called? Racemic. And does a racemic mixture ever bend light? Never does. Even though each molecule alone is chiral, have enough of its mirror image that cancels the other one out. Racemic mixtures do not bend light. Okay? So that is all with chirality and the rest.
Could you just define the racemic mixture one more time?
Yeah, a racemic mixture is a mixture that has the same amount of its mirror image as the main molecule. Or the enantiomers, right, both of them, there's an equal amount of both. So when I pass plain polarized light through it, sure, during the process of passing through, it's getting flipped and flipped. By the time it gets to the other side, nothing happened. Because one canceled out the other. So they do a racemic mixture doesn't bend light.
Just real quick.
Yeah.
So in order to be enantiomers, they have to be the mirror image of each other?
Yes, they have to be the mirror image, and they do not superimpose. Okay, so we're going to move on to the light and crystal field splitting theory. Okay? So the first thing I want to talk about, this should be really familiar to you guys from Chem 105, is the light spectrum. Okay, so the way I always remember it, you might have too, is just
Roy G. Biv, from decreasing energy to increasing energy. And what this is telling me is that violet and blue they absorb the highest energy light, which would be the shortest wavelength light. Vice versa for this end of the spectrum. So this is increasing wavelength and increasing energy. As we increase energy, we decrease wavelength. Okay? And so this brings us to the color wheel. Okay? What the color wheel tells us is that when we have certain molecules, they have the potential of absorbing certain light. And we're going to get more in depth with this later on with our molecular orbital diagrams. But just briefly with the color wheel. So for example, my shirt emits blue. Okay, so what color is it absorbing? Orange. It's absorbing orange. Okay, so my shirt, the molecules in it are absorbing orange light. And what we see that's emitted is the sum of the remaining colors. So if orange is absorbed, all we have to do is jump straight over across on the color wheel and say, okay, if orange is absorbed, then it's going to show blue. And that works for every single one on the color wheel. I can't guarantee if Dr. Macedoni will give you the color wheel. So I remember when I took this test, the first thing I did was on my scratch paper, I just drew the color wheel. Just make sure that I had that down and I didn't have to worry about it later on in the test. Yeah?
Do we know the wavelengths for each color?
No, I think I would know the relativity.
Okay.
Know the relative strengths, you know, blue compared to orange, but he's not going to make you memorize the specific wavelengths. Any more questions on this? And we're going to get into more application of this. Yeah.
Highest energy is violet.
Highest energy is violet. Yep. Lowest energy is red. Okay. I'm going to come back to magnetism. I just want to roll with this color stuff as we go. Okay. So this is something that Braden touched on with the ligand metal bond that we have going on with these complex ions. I just want to briefly explain to you guys exactly how it's working. This is something that you're going to get really in-depth in OChem, so I don't want to get too in-depth right now. I just want you to understand how these molecules are reacting. So I drew two molecules here. I have ammonia, and then I have a cobalt ion. Which of these is our Lewis base, and which is the acid? The base is our ammonia, because this has extra electrons, this lone pair, and our acid, you can think of it as electron deficient, that wants electrons. So what happens when this ligand metal bond forms is these electrons will actually move over and come and attach to that cobalt. So what you would have is you would have this ammonia, and this lone pair right here, these two electrons right there, what they did is they now made a bond to the cobalt. Okay, so that's what's happening here. Just so you guys can understand it kind of conceptually, is these lone pairs are making a bond. And when we have 6 of them on there, then we're going to get our big complex ion. All 6 of those lone pairs can come attached to that cobalt, and then we have, you know, the examples that Braden was going over. Does anyone have any questions on this?
Is that covalent?
Yes. Yeah, you can think of it as, yeah, what would you say, Brett?
For coordination bond?
It is. It's a metal ligand bond. I don't think the fact that it's covalent is going to matter. Because I know you're thinking it's like sharing electrons, but for this case, it doesn't really matter.
It's like a covalent bond.
Yeah.
So is this where the coordination number comes in, where you can stick 6 ammonias on there because it's...
Yes, so if I had 6 of these ammonias stuck onto this, our coordination number would be 6 in our coordination sphere. Okay, so now I want to talk about what exactly happens when we have this cobalt metal. Okay, and this has to do with how d orbitals are coming into play here. So I'm just going to say, for our purpose here, that we have 5 d orbitals in cobalt 3+. Okay? We have 5 d orbitals. Now, cobalt 3+, what I'm telling you here is this is just a flat line, okay? All of these electrons, they're all equal in energy level. And what happens when these ligands come in and attach is that the electrons that are already in this actually have some kind of repulsion. Okay? So these electrons are coming in, there's already electrons in here, and they repel each other a little. There's some repulsion. It still has enough energy for it to come in and stick, but there's going to be some repulsion there. So when we form this complex ion, what happens is when we have 5 equal energy levels here, what happens is it actually splits. Okay? It will split into 2 energy levels. And this is on the slides. You can see the way you might have saw the different lobes. I got the different lobes in the octahedral complex. And the most important thing to know, I think, is that this happens when the ligands come on. Okay? These will have different energy levels. Does anyone have any questions on this? Okay.
Should we memorize if it's like 5 for cobalt or whatever, any number for whatever?
Yes. So what I would do, I can't remember if I'm going to talk about it, but I'll write them up for you. If it's octahedral, I memorize this because I saw it on the slides. If it's octahedral, it's going to have 3 on the bottom and 2 on the top. If it's tetrahedral, it's going to have 2 on the bottom and 3 on the top.
So you should have that memorized for sure.
Planar is 2 and then
And planar is 2, 3, 4, 5. Yep. So just so everyone knows, this is octahedral, tetrahedral, and planar.